In the previous video, I derived the Euler equation for the continuous time Ramsey model. It looked like this. And in this video, I'm going to combine this with the budget constraint to derive the policy function for consumption. So remember, the Euler equation tells you how your optimal choice of consumption changes over time, but your policy function tells you your optimal choice of consumption at any point in time given your wealth. So let's derive that. And the way we do that is by combining the Euler equation with the budget constraint. So in the budget constraint, we obviously have the level of CT. In the Euler equation, we have the growth rate over time. So in order to plug the Euler equation into the budget constraint, we just need to integrate the Euler equation with respect to time. And if you do that, you just get CT is equal to C0 times e to the power of 1 over gamma times the integral from 0 to t of r s minus rho. So it doesn't look like we've done a whole lot here. C0 is unknown after all, but you'll see once we plug this in here, we can get an expression for C0. And I'm actually going to do this for the log utility case, so where gamma is equal to 1. So I'm just going to delete that there. And let me rewrite the budget constraint as well. Just replacing C with its definition, which was just this discount rate. And I'm just going to move the term involving consumption over to the right-hand side as well. So you can probably see why I've taken the logarithmic utility case, because now when we plug in CT in here, the term involving the integral of R is just going to disappear. It's going to cancel. You can do this with non-logarithmic utility as well. You just get a slightly more complicated expression. But let's plug in CT now. I'll just write it here. And we just get this expression. But this looks complicated because we've got nested integrals here, but actually none of the expressions inside the integral depend on the variables that are being integrated. So rho is just a constant, it doesn't depend on s, so evaluate that integral very simply. And C0 is also a constant, it doesn't depend on t, so we can also pull that out of the integral. So this term here is just going to be equal to e to the minus rho t, and I guess I'll write that here. And pull C0 outside of this integral. And just evaluate this with respect to t, and of course that just gives 1 over rho. Now this term here, I'm going to leave that like it is, but I'm just going to denote it as H0, because this is your human capital, if you like. It's the present value of all your labor income. So I'm going to call that human capital and denote it H0. And A0, of course, is your physical capital, your financial wealth. So just rearranging this, we get ultimately that C0 is equal to rho times A0 plus H0. But of course this holds at every point in time, so we can also just drop the zeros or replace them with t's. And it says that our consumption at any point in time is just going to be a constant fraction of our total wealth. And our total wealth is given by the sum of our financial wealth, A0, and our human wealth, H0. And the fraction is just going to be equal to rho. This is in the log utility case. So this is the policy function under log utility. With more general CRA preferences, this rho, this marginal propensity to consume, which is what it is not going to be a constant. It's going to depend on R. And if R is varying over time, it's going to depend on all the future values of R. So that's why I wanted to look at the log utility case, because that's just far simpler. But you can certainly do the more general case. So in the last few videos, we've derived the Euler equation, which remember just tells us how our optimal choice of consumption grows over time, or changes over time. we found our policy function for consumption, which was just that in the log case, consumption was just a constant fraction of our total wealth. This is for log utility. And we have our budget constraint, and I'm just going to write this as the flow budget constraint, which remember was just AT dot equals RT times AT plus YT minus CT. Now, if we want to solve the Ramsay model more fully, we're going to need to combine these optimality conditions and budget constraints for the household with optimality conditions for the firm side of the economy. And that's going to give us that the interest rate, if we have a Cobb-Douglas production function, is just going to look like this. It's going to be the marginal product of capital less the depreciation rate. And our YT up here, which is really just the wage, so perhaps I should have denoted it with a W instead, that's going to be equal to the marginal product of labor. That's the wage, and these are both from the firm's first order conditions. And we also know from market clearing that the household's wealth is going to be equal to the capital stock of the economy, assuming there are no other assets that the household can save in. So combining the Euler equation with the budget constraint with these three conditions, with the firm's optimality conditions and the market clearing condition, we can get two equations that totally define the dynamics of this economy. We have the Euler equation, but this is now for the economy as a whole rather than just from the household's perspective. So sometimes this is called the Keynes-Ramsay rule. And we have our resource constraint for the entire economy, which shows us how the capital stock evolves. And of course, if you rearrange this just gives the goods market clearing condition that consumption plus investment, which is K dot plus delta K, is equal to output, which is just K to the alpha. So these two differential equations completely describe the dynamics of the model, and given an initial condition, K0, and a terminal condition, which is our transversality condition, which remember looked like this. Where now I've just replaced wealth with the capital stock. This will allow us to find the optimal path of consumption and capital from any arbitrary initial condition for our Ramsay economy. And in the next video, I'm going to show you some phase diagrams, which are graphical representations of these dynamic equations, which hopefully give you a little bit more intuition about what these equations actually mean for the optimal paths of consumption and capital. So thanks very much. I'll see you in the next video.